The Economy of Decompression by Dr. Frans Cronje. The story of decompression, its illnesses and the attempts to avoid them, in a sense is a story of excess and debt. In a word, an economy. An economy surrounding the exchange of gases that are neither involved in nor required by our metabolism, those that make up the balance of pressure in our lungs, allowing us to breathe while we dive. In 1854, two French physicians, Paul and Wattel, after observing a variety of illnesses suffered by men tilling coal inside pressurized containers or caissons in the French marshlands, established a primary caveat, that decompression illness is a sickness of decompression. One pays only upon leaving. The time and pressure of the exposure to compressed gas, as well as the rate and duration of decompression to the surface, were the primary determinants of one's fate. Yet even then, it was understood that all men were not created equal. Some suffered more severely from symptoms of decompression, while others appeared more hardy. This variable susceptibility between individuals, and even the same individual from day to day, has remained one of the biggest challenges to solving the riddle of decompression illness to this day. I have been set the rather ambitious task of explaining the strategies for avoiding decompression illness, what the basis of these prevention strategies are, the seemingly endless barrage of mathematical and statistical methodologies that we call decompression algorithms. I can offer no apology for the fact that some of this is rather confusing. However, what I hope to achieve is at least offer an index to the apparent chaos. Importantly, we have to realize that none of the decompression algorithms have anything to do with human physiology. They represent an imperfect but practical tool for managing decompression or decompression risk. Much like a compass allows us to navigate without us understanding why it points north. Behind the somewhat complicated mathematics of decompression theory lies a rather basic understanding of gas exchange and its interaction with the body. This can be summarized in 5 primary concepts. Firstly, we absorb inert gas at increased ambient pressure in a seemingly exponential way. Secondly, we eliminate inert gas when ambient pressure drops, but at a slower rate than we absorbed it. We do have the option of manipulating the gas mixtures we breathe to speed things up, though. Thirdly, during decompression, inert gas tissue tensions rise relative to the falling ambient pressure and the inspired inert gas partial pressure. That is when tissue gas tensions exceed the ambient pressure. A so-called state of supersaturation then exists. Fourthly, once supersaturation occurs, bubble formation may result. And fifthly, if the volume or the location of these bubbles exceeds some critical quantity or volume, symptoms or injury will occur. So now the objective of decompression algorithms is to control for these factors to avoid the biological consequences of decompression. In a word, a decompression algorithm is therefore a mathematical model or scheme for predicting inert gas flux within the body within certain narrow parameters, in the absence of actual real-time measurement and verification. They basically render biological complexity to a workable formula. There are 2 broad categories of decompression modeling that have appeared over the past century. One is aimed at modeling the actual inert gas flux and the determinants of bubble formation within the body. It assumes that as long as certain principles of inert gas exchange are observed, decompression illness can be avoided with reasonable certainty. Most decompression algorithms, and certainly all the original decompression algorithms, have been based on this precept. A second model considers the probability of developing decompression illness in relation to a large range of exposures. It still examines the principal features of inert gas kinetics, but it then expresses these in terms of the probability of developing symptoms rather than quantifying the inert gas parameters as such. Let me briefly cover the postulates common to the so-called deterministic models for decompression. The objective of deterministic models is to avoid symptomatic bubbling by controlling inert gas in two ways. Firstly, either by determining tissue gas content, or, secondly, by predicting tissue gas or bubble volumes. Tissue gas content models focus on preventing a critical level of supersaturation in tissues, whereas bubble models focus on preventing critical numbers, volumes, or sizes of bubbles. The father of the original deterministic model is John Scott Haldane. He fashioned the concept that inert gas flux could be modeled based on pharmacological principles of absorption, distribution, metabolism, and elimination. Note that, by definition of course, inert gas does not participate in the body's metabolism. However, its absorption and elimination is potentially affected by other biological gases like oxygen and carbon dioxide that indeed are metabolically active. Since 1906, just about all deterministic decompression algorithms have used this approach to predict inert gas uptake and elimination, so-called inert gas kinetics. More recently, the importance of inert gas bubbles interacting with the body has also been modeled, that is, inert gas dynamics. So kinetics relate to uptake and elimination, dynamics to interaction with the body. Most tissue content models use this equation or its derivatives to describe inert gas uptake and elimination as a function of ambient pressure, tissue solubility, and blood flow. The greatest debate in this area has been how long it takes for the body to saturate completely, which of course also determines desaturation. This has ranged from Haldane's original 6 hours to Bielmann's eventual 6 days for the slowest parts of the body. All tissue content models have assumed an exponential uptake, that is, a constant ratio. More recent models have used slower and even linear eliminations, in other words, constant rate. Just to elaborate on those concepts for a moment, exponential changes share the common feature of constant ratio of change over time. So, to make exponential changes easier to deal with, we use the concept of half-times. That is, the time it takes for half of the change to occur. 50% saturation in this particular case. It will then take another half time for the remaining 50% to change by half, which then would represent 75% saturation, and so on. For all practical purposes, it takes 6 half times for an exponential process to be completed, at least to 98.5%. Conversely, linear change means that the change occurs at a constant rate over time. In the process of defining the range of factors that affect the absorptive capacity of tissues to accumulate inert gas, as well as the distribution of inert gas to them through either circulation, called perfusion, or simply the flow, called diffusion, tissue content models divide the body into distinct homogeneous zones. They are theoretical and have been called tissues, compartments, tissue compartments, half-times, or time constants by respective modelers. Essentially, they indicate how quickly inspired inert gas partial pressure equilibrates with the tissue gas tension in various parts of the body. Over the past century, the equilibration times have ranged from Haldane's original 5 tissues, which were 5 to 75-minute half-times, to Bielmann's 16 tissues, which went from 2.65 minutes to 635-minute half-times. Most computers in use today use 8 tissue compartments, which range between 4 and 635 minutes. For most models, these tissue compartments function in parallel, meaning they absorb inert gas independently without affecting one another. Conversely, the British, which is the Hempelmann, and the Canadian, which is the Kidd-Stubbs models, have considered serial or sequential interactions ranging from 1 to 4 tissue compartments. However, the problem has never been getting inert gas in. It has been getting it out without biological damage. So how do we make decompression safe? It brings us back to the dichotomy in the models. Do we model gas content, bubble volumes, or even both? And then, how much is too much? Let's start by considering the options available to the tissue gas content model. In this theoretical presentation, we initially have an increase in ambient pressure during the dive. Tissue gas tension does not increase immediately because it requires Henry's law to ultimately start dissolving. However, over time, the tissue gas pressure will increase. The critical point to consider, though, is the ambient pressure line, because the point where tissue gas pressure exceeds the ambient pressure line is the threshold for bubble formation. As the individual starts to ascend, the tissue gas pressure may start to exceed the ambient pressure line. The critical issue of this, which is called supersaturation, is the particular point where bubbles would actually form, and of course, whether the tissues in which they form would be sensitive to damage as a result. Assuming that different parts of the body absorb inert gas at different rates, there is therefore a spectrum of tissue saturations at the end of a dive, unless of course the dive has been so long that all the tissues are saturated. As decompression occurs, there is a decrease in ambient pressure, which results in the tissue pressures approaching, and in some cases exceeding, the ambient pressure line, which again is called supersaturation. Now, the question is, how much can inert gas tissue tensions exceed ambient pressure? What constitutes critical supersaturation? Haldane's hypothesis was that it should not exceed the so-called 2-to-1 ratio. That was his so-called 2-to-1 concept. Based on this principle, depth would determine the amount of supersaturation that could be tolerated. The system works, but only up to about 6 atmospheres. You could not, for instance, decompress from 190 meters or 20 atmospheres to 90 meters or 10 atmospheres. To do so instantaneously, you would suffer biological damage. So a different strategy is needed for deeper dives and for greater levels of slow tissue saturation. Over time, observations led modelers away from the blanket 2-to-1 ratio. More supersaturation was permitted in the so-called faster tissues than in the slower ones. Ratios eventually ranged from more than 4-to-1 for the fast tissues to less than 1.4-to-1 for the slow tissues. Bielmann introduced slightly greater sophistication to this concept by introducing 2 factors, the so-called A and B factors, that determined the minimum depth to which a safe ascent could be made. Using these revised ratios, modelers then mathematically developed ascent rules based on these maximum permissible supersaturations for any depth and any tissue compartment. In practical terms, the ascent was based on the following principle. Using whatever method the modeler chose, a critical level of tissue supersaturation was defined. This, in effect, became a limiting line for that tissue compartment. Bearing depth, time, and ascent rate in mind, decompression was considered safe if it kept all tissues between the supersaturation and the limiting lines. If, for a given ascent rate, no tissue were to exceed the limiting line, a dive would be a no decompression dive, as illustrated here. In this case, during the ascent, even though there is an increase in tissue pressure and it exceeds the ambient pressure line, it never exceeds the critical supersaturation line and therefore is a no decompression dive. If, conversely, a tissue pressure reaches the limiting line, a stop will be required. The stop would then permit a reduction in tissue pressure whilst maintaining ambient pressure until it became possible to make a further ascent while still remaining within the limiting line. And this is essentially how staged decompression emerged. The one factor not accounted for in the tissue content models is the effect of bubble formation on decompression. It is known, for instance, that diving to as little as 3 meters can cause bubble formation. And the presence of bubbles radically changes the outgassing kinetics. Interestingly, though, bubbles are actually a very effective carrier of inert gas within certain limits, such as the ability of the pulmonary circulation to eliminate them, and in the absence of shunting, whereby bubbles could be transferred into the arterial system and cause embolism. Otherwise, bubbles actually speed up the decompression process and may do so safely. However, once a critical volume or quantity of bubbles is reached, outgassing may then again be slowed due to the impact that the bubbles have on circulation or perfusion. So again, it is a balance that is required to account for these. The matter of controlling bubbles becomes quite complex. Basically, it operates on the principle that bubbles grow when tissue gas pressure is greater than inert gas partial pressure within the bubble. So in other words, when the tissue gas pressure is greater, there will be an influx of inert gas into the bubble. This is determined by the ambient pressure and bubble size. Bubbles tend to collapse due to surface tension, but at some point the surface tension may be overcome when the bubbles start to grow. In other words, the larger a bubble is, the less the impact of the surface tension is, and the more likely it will grow rather than collapse under the effect of the surface tension. The critical radius has been calculated to be around 0.72 microns. In order to prevent large numbers of bubbles, permissible supersaturation in bubble models are less than for content models. In other words, bubble models are typically more conservative in terms of the no decompression limits, ascent rates, and the stops required. There are two bubble models that are worth mentioning in particular, those of Junt and Vinke. Junt developed the original bubble model, but he had no method to deal with repetitive dives. So the outcome of all the mathematical crankings was more conservative no decompression limits up to 42 meters seawater when compared to the US Navy table. Vinke took it a few steps further by reducing critical gradients and creating a method to account for repetitive dives. In short, there were shorter no decompression limits, deeper stops, and slower ascent rates, but unfortunately, after all the mathematical cranking, an apparently higher incidence of decompression illness occurred based on the reported use of his table. So now on to the other way of dealing with decompression illness risk, the so-called probabilistic modeling. The risk of decompression illness is somewhere between 0, which means it never happens, and 1, which means it always happens. And by developing a so-called risk function by means of comparing the mechanics of a given dive profile, that is the depth, the time, the breathing gas, and so on, to the incidence of decompression illness data, using anything from very simple to very complex methods, it is now possible to then predict the probability of sustaining decompression illness. Initial efforts by the US Navy were called the maximum likelihood method. Initial models had an all-or-nothing approach. The next step produced the US Navy 93 tables, which used a 1, 2.3, or 5% probable incidence of decompression illness. The biggest challenge has been calibrating the model with enough safe dives, rather than only high-risk dives that are highly likely to produce decompression illness. The most sophisticated model for predicting probability of decompression illness immediately following a dive and subsequently was produced by Wayne Girth of the US Navy. DAN is submitting its data, collected through Project Dive Exploration and Dive Safety Laboratory, to expand the database for this model, in the hope of ultimately providing a reliable method of predicting decompression illness. So, where does all this leave us today? Have we in fact successfully unraveled the mystery of preventing decompression illness with all these strategies? Of course the answer is no, but the reason for the failure unfortunately is not that obvious. In beating bubbles, we need to realize that there is more to this than mathematics. We also need to remember that there are issues surrounding the formation and migration of bubbles, as well as bubble-related interactions, all that affect the outcome of a particular decompression. So we should not purely focus on the cause, but also on the effects of decompression. Not all bubbles cause bends, and we therefore also need to understand why not? Manipulating bottom time, ascent rate, and stops, as well as the ongoing trade-off between establishing steep gas gradients to expedite inert gas without increasing the risk of bubble formation, remain big pieces of the puzzle. However, we also have to be aware of the mysterious individual factors that are a source of seemingly never-ending speculation and study. Because decompression illness is relatively rare, we are still unable to answer many of these questions scientifically. For instance, does obesity increase the risk of decompression illness? Possibly, but we don't know for sure. Does gender affect the incidence of decompression illness? At the moment we don't think so, but we don't know, and the list continues. We also need to realize that once bubbles have formed in the body, they may migrate through the circulation and reach other tissues that may be more vulnerable to bubble-related injury. This is particularly true when bubbles formed in venous blood, which is a common finding even after relatively short and shallow dives, are transferred to the arterial system and travel to the heart, the brain, and other vulnerable organs. This transfer may occur due to short circuits between the lung and the body's circulatory systems, or if the microscopic blood vessels in the lung are unable to eliminate them effectively for whatever reason. Finally, we have to contend with the fact that the interaction between the body and bubbles may be variable. For the same amount of bubbles, some people develop symptoms while others don't, even in the absence of any evidence of shunting. We believe this to be true due to variable reactions to bubbles. If so, these risk factors might be identified and managed. Some recent research has suggested that certain forms of exercise, or even taking certain homeopathic medications before diving, may affect the body's reaction to bubbles. Similarly, bubbles themselves may vary in how they affect the body. They may block, break, or bother the body in different ways. But if we have a better understanding of what these factors are, we may again have the opportunity to prevent this, independent of the presence of bubbles. So, the pursuit of a sound strategy to get back to the surface safely continues. Are there additional empirical changes we can make to improve the safety of diving? Yes. Our group has looked at the effect of empirical deep stops on a 25-meter dive profile. I must emphasize that this presumes diving within generally accepted no decompression limits, ascent rates, and it only applies to that particular depth studied, which was 25 meters or 80 feet. Without going into too much detail about the findings, the following summary represents, at least from a biological rather than mathematical perspective, the best ascent strategy we can offer at this time, based on the collective Doppler bubble scores for a 25-meter dive conducted within no decompression limits. Firstly, a deep stop for at least 2.5 to 5 minutes at 15 meters. Note that we found 1 minute was too short. Secondly, engaging in a second shallow stop of 3 to 5 meters for 3 to 5 minutes, which should be at least as long or longer than the deep stop. So if the deep stop was 3 minutes, the shallow stop should be 3 minutes or longer. And finally, ascending at 10 meters a minute. It's interesting that the ultra-slow ascents were not biologically superior. In fact, on the contrary, they appeared to produce even more bubbles, even if the overall time for returning to the surface was the same. So that is what I mean by economy of decompression. It is not only a matter of how much time you spend, it is also how you spend it. I hope this has given you a fresh look on the science behind the decompression tables. The bottom line is that there still are no guarantees. So if you are a DAN member, thank you. If not, we recommend you join.